All right. So I posted a bunch of new problems and I've assigned a couple of them so far. And there are no solutions posted for those yet because I haven't done them yet. My plan is either Tuesday or Thursday of next week. We'll spend a class doing these homework problems. We won't go through all of them, but we should be able to get through a lot of them. So homework problems on the Rankine cycle. And so, you're right, it's Thanksgiving next week. Yes, you're right. Yeah, we do have class Tuesday, but not Thursday. Yeah, you're right. Well, anyway, so either Tuesday of next week or the next Tuesday or whatever. So I think the way to get the most out of that is, work on those problems, try to do them without the homework, and then you can sort of compare your answers as we go through them in class. I was just saying, one of the next couple classes, I'm going to, in class, go through solutions to some of those new homework problems because I don't have them yet. So yeah, and if, like always, if you want to wait to turn your homework in, feel free, or it doesn't, I'm just scoring those like you did it or you didn't do it anyways. So it's not like you're going to lose points if you turn it in before, but
for the daily assignments?
For the daily, yeah.
Yep.
So, okay. So that's what I'm going to do with those problems that don't have solutions yet. And it's going to be a similar thing when we get to refrigeration cycles, because I'm going to have to post a bunch of problems I don't have solutions for to that too. Okay, so today we're going to talk about incorporating irreversibilities into the calculation. And then incorporating superheat and reheat. So the first one of these irreversibilities is just a way of getting more accurate answers, more realistic answers. And then the second one is sort of about power plant design, a couple of things that make power plants run more efficiently. Okay, so first, irreversibilities. The two isentropic processes in the ideal cycle produce entropy, in real life. And so this is kind of what we're looking at. So here's a TS diagram. So the ideal cycle that we've been dealing with looks like this. We have state 1 up here, and then it goes through that isentropic turbine. And then it goes through the condenser to the state 3. I'm leaving off the state 2 for a second. I'll deal with that in a second. And then it goes through the isentropic pump. I'm going to leave that off for a second too. Okay, so that's the ideal cycle. That's what we've been doing so far. In real life, what happens is this turbine process actually looks like this on the diagram. So this is the state 2. Okay. This, and you can see that there's an increase in entropy, a small increase in entropy as you go through that turbine. This, what was our state 2 in the ideal cycle, now we're going to call it state 2s for, constant entropy. And going through the pump, that's the other one that we've been assuming is isentropic. Instead of that being an isentropic process like this, it produces, again, a little bit of entropy to there. So this is the true state 4. And this black one that was our state, that's been our state 4 up until now, I'm going to call the state 4s. Okay, so you can see where that entropy comes into those two processes, because the horizontal axis is entropy, so you can see that each one of those two processes increases, a little bit, increases entropy a little bit. And the way this is represented mathematically is called isentropic efficiency. So I'm going to go through the turbine first and then go through the pump. So for the turbine, the isentropic efficiency I'm going to call it eta sub t, and it's equal to the work rate for the turbine divided by the work rate for the turbine assuming isentropic. Which, of course, we've used this little mathematical trick a lot since we've represented everything in terms of the work rate per mass flow rate. You can also write this as the ratio of the mass flow rates for these two things. And now we have expressions for both of these two. So we can write this as the enthalpy at state 1 minus enthalpy at state 2 divided by enthalpy at 1 minus enthalpy at 2s. So if you're given like a fraction or a percentage of that isentropic efficiency, you can rewrite this equation as H2, the true H2 is equal to H1 plus the isentropic efficiency times the quantity H2s minus H1. Okay, so the idea here is, say you're given that this turbine has a isentropic efficiency of 90%, say, Well, you can do the calculations for the ideal Rankine cycle and then do this correction to find the enthalpy at the state 2. Okay, then that enthalpy that you can calculate using the isentropic efficiency is what you would use to calculate the thermal efficiency of the whole cycle. Okay, and it's similar for the pump. So the isentropic efficiency of the pump so it's eta sub p, and this time notice that this is kind of fundamentally different than the work for the turbine, because the turbine work is what we're getting out, the pump work is what we're putting in, and so that switches the reciprocalizes the fraction for the efficiency. So we have W dot for the pump. For the ideal case, divided by W dot for the pump in the true case. That's switched from what it was before. And you can write these as ratios of the mass flow rate and you can then, now that we have it this way, we can write it in terms of the enthalpies. So you have H4 for the ideal case minus H3 divided by H4 actual minus H3. And one other thing, remember that we also can write these for the pump because we're assuming that this is liquid and it's incompressible. We can also write this as V3 times the quantity P4S minus P3. So that was that other way we had to calculate that rate, divided by, well, the V3s are the same, real and ideal. So V3 divided by V3 times the quantity P4 actual minus P3. Those V's cancel. And so you can also write this as, so this is that isentropic efficiency. And you can also write it as the ratio of P4S minus P3 divided by P4 minus P3. So the S's are ideal, the S's are what we've been dealing with up until now, and the non-S's are the actual case with entropy in these processes. And so now we can rearrange, just like we did with the turbine, we can rearrange to find the new true states at state 4. So if you know eta for the pump, then you can calculate H4 is equal to 1 over eta pump times the quantity H4S minus H3 plus H3 Or alternatively, using that incompressible assumption, P4 is equal to 1 over eta P times the quantity P4S. You guys didn't think that was funny? Eta P? Like,
Sorry, I'm slow this morning.
P4S. Okay, it's not that funny. But, okay, minus P3 plus P3. Okay. So yeah, the basic idea is if somebody has done the measurements of those isentropic efficiencies, you can do all your calculations for the ideal case, like we've already done, and then like apply these correction equations to find what the true states are after each of those two, after the pump and the turbine, and then we can plug those into the total efficiency and do equations with those properties. So let's go back now to this same. So back to the example from last time. And remember that last time we assumed this was an ideal cycle. So all our answers were for an ideal cycle. And so I'm going to use the calculations that we did last time to be now our S states. Okay, you with me on that? Because we were doing the ideal case. So now that's our 2S and our 4S. So state 2 from Tuesday is now our state 2S, and our state 4 from Tuesday is now our state 4S. Okay, so this, let's see, what do I have to say about this problem? So let me just summarize this. So it was a steam vapor cycle. Saturated vapor entered the turbine at 8 megapascals. Saturated liquid exited the condenser at 0.008 megapascals. The net power output was 100 megawatts. and we calculated the thermal efficiency the back work rate, the mass flow rate, the rate of heat transfer in at the boiler, and the rate of heat transfer out at the condenser. And then we did the thing with the cooling water. I'm not going to do that again because the condenser isn't affected by this at all. This only deals with the two isentropic processes. So calculate these again. Assuming isentropic efficiencies at the turbine and the pump that are the same and equal to 0.85. Okay, well, when we did this problem before, we got, so I'm just going to summarize our results from Tuesday. The enthalpy at state 1 was 2758 times 10 to the third. The enthalpy at state 2 that we found, now that's our 2s, and that's 1795 times 10 to the third. H3 coming out of the condenser was 173.88 times 10 to the third. And H4, now our 4s, was 181.87 times 10 to the third. And what we got, so this is now what we're going to compare. We calculated, oh, did I not write these down? Any of you guys have your notes from last time in front of you? I guess I have mine right here. Let's see. So what we got was, oh, I do have it. I do have it, maybe, no. Okay, I have it right here. So we have what we got last time was a thermal efficiency is that what it was? 0.371, yeah. So we got a thermal efficiency of 0.371. We got a back work ratio of, what was that?
8.31 times 10 to the
Fifth or third? Okay, minus third. And then what did we get for the rate of heat in at the boiler? I don't think those are going to change anyways, but we.
Rate of heat at the boiler was 176.
270 E6. Okay, and then the rate out at the condenser was
170 E6.
170 E6. And the mass flow rate is the last thing. 104.7. That's kilograms per second. Okay, so let's think about what we expect to happen now that we have this inefficiency introduced. What about the thermal efficiency? Is that going to go up or down? Down. I would think, like all the temperatures are the same. Back work rate, up. These two,
Those should change if they are dependent on enthalpy.
Yes, correct. So you can just look at the equations for QB and QC rates over mass flow rate, and you can see that they do have H2 and H4 in them, and those are going to change. So we know that they are going to change. Well, do you expect the rate of heat coming in at the boiler to go up or down? Up. That's what I would think too. Yeah, up. And then at the condenser?
Down, up, or up.
I don't really know. I think I would say up too. You'd have to get rid of it anyway. Yeah, seems like a good hypothesis. I don't have an answer for you yet, but we'll find out. And then mass flow rate, to get that same amount of power out of it, you'd think you'd need more mass flowing around?
Yeah.
Okay, so let's find out.
The reason for calculation is that's our hypothesis.
Yeah, exactly. Okay, so first we can calculate H2. So H2 is equal to H1 plus 0.85 times the quantity H2S minus H1. And so that's equal to 2758 times 10 to the third plus 0.85 times the quantity, 1795 times 10 to the third minus 2758 times 10 to the third. And you get an H2 I got 1939.45 times 10 to the third. Is that what you got?
Yeah.
And we can do the same thing for H4. So H4 is H3 plus 1 over 0.85 times the quantity H4S minus H3. And so H4 173.88 plus 1 over 0.85 times the quantity 4S 181.87 times 10 to the third minus 173.88 times 10 to the third. I got 183.28. Is that what you got, Cole? Yeah.
Yeah, I got it.
Okay. And now we can use our calculation. So now for part A, now that we have the true enthalpies at those states, our thermal efficiency is 1 minus H2 minus H3 over H1 minus H4. So that's 1 minus 1939 0.45. I'm going to leave off the 10 to the thirds because it's just a ratio here. Minus H3, 173.88. Divided by 2758. Minus 183.28. And you get 0.314. So you start with the same boiler temperatures and everything. The condenser and boiler work exactly the same as they did before, but you have those efficiency losses in the pump and the turbine, and it decreases your thermal efficiency from 0.37 to 0.31.
Wait, just to reiterate then, so the eta, P and eta T are just referring to the processes done by the boiler and the compressor, and then this eta is the entire cycle?
This 8 is the entire cycle, yep, and the
Okay.
and the other two are just for the two isentropic parts, which is the turbine and the pump.
Yeah, which, well, were isentropic, but in this case.
Correct.
Oh.
Yes. Right. The back work rate. So, or back work ratio, I guess it is calculated H4 minus H3 divided by H1 minus H2. And so that's 183.28 minus 173.88 divided by 2758 minus our new H2 is 1939.45. And so the back work ratio is 0.01, I guess 1.5. So we can think of that as 1.15 times 10 to the minus second. So these first two went the way we all expected them to. You have less efficiency, so you have less total thermal efficiency, and the pump is using up more of the power than, a bigger chunk of the power than you were before, of the power that you get out of the turbine. Mass flow rate. Well, we know that 100 times 10 to the 6 is the work rate at the turbine minus the work rate at the pump. And so that's equal to the mass flow rate times the quantity, H1 minus H2, because that's the rate of work produced at the turbine divided by the mass flow rate, and then minus the expression for the pump. So minus H4 plus H3. So the mass flow rate is 100 times 10 to the 6 divided by the quantity, H1, so 2758 times 10 to the third, minus H2 minus H4. So minus 1939 minus 183, was it? Okay, and then plus H3, 174. Oh, and these are all times 10 to the third. And so the mass flow rate is 123.5 about kilograms per second. We had 104 or something before, right? So in order to get this much power out of the less efficient thing, you have to have more working fluid moving around. And then, well, now these last two are pretty quick. So the heat coming in at the boiler is the mass flow rate times the quantity H1 minus H4. So that's 123.5 times the quantity 2758 times 10 to the third minus 183 times 10 to the third and we get 318 megawatts. For the ideal case, we had 270. So you need more heat coming in at the boiler. And then at the condenser, the last one, the heat out at the condenser is equal to the mass flow rate times the quantity H2 minus H3. So that's 123.5 times 1939 times 10 to the third minus 174 times 10 to the third and we get 218 megawatts. Okay, so with decreased efficiency, and with the same boiler and condenser, states for the same net power, our thermal efficiency was down, our back work ratio was up. What was the next thing we calculated? Mass flow rate. Our mass flow rate was up. Our heat rate coming in at the boiler was up. And our heat out rate at the condenser was up. Any questions about doing those?
Are you concerned at all with, what was it? The heat or mass flow rate of the condenser for other liquid going through, the cooling liquid?
That's a good point. So I said let's not do it because, you know, I thought the condenser isn't going to be affected at all, but it turns out like we needed more heat to go out at the condenser. Yeah. So yeah, we would have to put more, more cooling liquid through to pull more heat out.
Oh yeah, there's right here because M dot goes up and then H2 goes up.
Yeah,
it's directly proportionate for the mass cooling.
Right. So we could do that, but I've sort of lost my enthusiasm for this problem. Okay, so any other questions? All right, so then the next thing is superheating and reheat. So I mentioned these before. These are two ways to improve performance over the cycle that we've discussed so far. Okay, so let's start with superheating. So the idea of superheating is instead of heating the working fluid at the boiler to a saturated vapor, go from the boiler to a superheater, and this two-stage thing here is called a steam generator. To make the working fluid a superheated vapor. Well, you know that if this increases the average temperature of the boiler, which we already talked about, improves the efficiency of the whole cycle. So this increases cycle efficiency. So this is what it looks like. So in the cycle that we've talked about so far, this would be state one over on the right side. That would be a saturated vapor. But now from here, it's going to, instead of going straight into the turbine, it's going to go through the superheater and increase past that saturation point. And then, so state one is up here. And then it's going to drop down to state two, go through the turbine. Everything else stays the same. So this is the condenser. It comes out of the condenser as a saturated liquid. Then it goes through the pump to state four. And then this sort of three-leg trip in the boiler means that it starts out as a compressed liquid. It gets heated up at a constant pressure until it's a saturated liquid. then it changes phase until it's a saturated vapor, and then it superheats to become a, a superheated vapor. And then this idea, you can combine it with reheating. And let me draw that, and then I'll explain like all the whole. So first, let me draw what's happening in the, like physically in the cycle if you have a reheat. So this is the steam generator. We're going to use superheated vapor again. And the steam generator sends this superheated vapor through the first stage of a two-stage turbine. Okay, so this is where the work is coming out. As the working fluid comes through the first stage turbine, it goes back to the steam generator, gets heated up again, and then gets sent back to the lower pressure second stage turbine. Through that second stage turbine, now everything looks the same as we're used to. It goes through the condenser. I guess I usually put that on the bottom. And then through the pump and back to the steam generator. The working fluid in that first stage turbine has a high pressure. The one in the second stage turbine has a lower pressure. The benefit of this is, so we talked about that increasing the pressure in the boiler increases the overall efficiency of the power cycle, right? But there's a practical problem with high pressure coming into the turbine, and that is that when the pressure is really high, what happens to the boiling point of water? Does it go up or down?
Yeah.
It goes down. No, it goes up. If the pressure goes up, the boiling temperature goes up. Okay, like if you're climbing Mount Everest, you can't make pasta because it boils at 70 degrees or whatever. So, so the idea is the benefit of this is in the high pressure first stage turbine. The boiling temperature is really high. And that means that you're likely to have liquid, get back to the saturation temperature and have a mixture of liquid and vapor in the turbine. And that's not thermodynamically bad, but it's bad for your turbine. Okay, so you can get a lot of liquid in the turbine, which is bad for the blades. So by reheating this vapor, you can keep that from happening and save maintenance on the turbine. Okay, so here's what this looks like on a TS diagram.
Wait, so that's real quick, the stuff going back in to get superheated, it's going to be since you have a vapor liquid mix, it's going to be mostly that liquid going back through to get superheated?
So ideally, I'm going to draw a picture right now, and let me just draw this picture, and then we'll talk about it as we look at the picture, because you can actually see what's going on. So here's the TS diagram. Here's the first superheating. I have to make this a little shorter. Okay. And I'm going to call this stage 1A. Okay. Now from 1A, it goes back into the steam generator. It can get back to saturation or stay a superheated vapor. But it gets here to what I'll call state 2A. Now it goes back to the steam generator and the temperature goes up again. I'll call that 1B. And now it goes through the second stage turbine and gets back past the saturation point. 1B. And so this is the state 2B. And now everything else stays the same. Here's the state 3. Here's 4. Okay. And this little this 2A can be in the mixed region, or it can be in the superheated vapor region. But either way, sending it back to through that steam generator keeps the liquid in the boiler from going as far into the past the saturation point. So it keeps it from becoming liquid, or from becoming very much liquid. Yeah, I know. Okay, so let's start at the boiler. Okay, so that's it enters the boiler at 4. Okay, and at 4 it's a compressed liquid, and it heats up until it's a saturated liquid here. Okay, and then it changes phase until it's a saturated vapor here. And then the superheater brings it past the saturated vapor into a superheated vapor. Okay, and so now we're done with the steam generator, the whole steam generator, and we're at this point 1A. And we're ready to go through that first high pressure turbine. Okay, so now I've drawn it as isentropic again. But it goes through that first high pressure turbine from 1A to 2A. And then from 2A to 1B it's heading back to the steam generator for the temperature to increase again. And it takes this other jog back farther into the superheated vapor region.
Okay, so yeah, so going from 1A to 2A then, you pretty much you get work out of it from the turbine, but right right to the point where it crosses the threshold
Right.
where you're getting water again, you then feed it back.
Yes,
Okay.
that's right.
Otherwise, you would have, if you have a single turbine, it would go straight from 1A downward.
All the way down to 2B, or
Or just
not quite a 2B, but just to the left of 2B, correct?
Which would then mean that you have a greater water to vapor ratio in
Yes,
the turbine.
exactly.
Because the further you are to the right, the lower that ratio is.
Exactly.
You want to move 2B to the right.
Yep. And you still have to do that from 1B to 2B, but remember that second stage turbine doesn't have as high a pressure.
Yeah.
So
it's not going to be as affected.
Yeah,
Or have its poor performance from that the liquid running through it.
right.
Okay. Whereas, the first turbine from 1A to 2A, you can or engineer it in such a way that you don't think about liquid whatsoever. It's all
Right.
just about the steam.
Yeah, exactly.
Okay.
Okay, so let's, let me just write down the steps from the different, so here are the states. So let's go, so here's 1A, 2A, 1B, 2B, 3, and 4. And we'll talk about what we know at all of these things. So from 1A to 2A, that is the high pressure turbine. We're going to assume that that's isentropic, although you could make the corrections using the isentropic efficiency. From 2A to 1B, it goes back through the steam generator. So that's a constant pressure through the steam generator. From 1B to 2B, that is the low pressure isentropic turbine. From 2B to 3 is the condenser. I'll write constant pressure on that again. And then from 3 to 4 is the isentropic pump. So the next thing we're going to do, I'm going to wait until next class to do this problem, but we have one more sort of longish problem that's going to use similar parameters to those last two examples we did. And so we'll do this example problem. So we're still going to have the steam entering the first stage turbine. at 8 megapascals. This time, since it's not a saturated fluid, we have to know the temperature too in order to look stuff up. So we're told that the temperature is 480 Celsius. And it leaves at 0.7 megapascals. It's reheated to 440 Celsius. And then goes through the second stage turbine. And it exits the second stage turbine at the low pressure that we've had in those other example problems, 0.008 megapascals, lower than atmospheric pressure. Net power output is 100 megawatts again. And we're going to basically do all those same calculations again. We're going to calculate the thermal efficiency, the back work ratio, the back work ratio, are we? It was mass flow, but actually I'm just thinking for a second because it doesn't have a back work ratio on there, but we could still calculate that. Then the mass flow rate, yeah. And then the heat transfers at the boiler and the condenser. And hopefully we're going to see that the efficiency goes up again. The back work ratio goes down, and in order to produce that same amount of net power, we have less heat transfer at the boiler and less heat transfer at the condenser.
Yeah, so overall we'll see that this is better than the single stage turbine.
Right, yeah.
Can you go back up to the numbers, like 1A to 2A and 2A to 1A?
Oh, yeah. I don't know why I wrote those so small, but.
So how is the reheat from 2A to 1B at constant pressure? Does it only go through saturation? Or is this some like magical balloon superheat system that doesn't increase the pressure?
So it's going back into so if you just have if you have steam, oh, that's a good question. So if you have a fixed volume and you have steam and you send it back, you have steam and it fills the room and then you keep heating it up, that pressure is going to go up. I'll have to think about that later.
Okay.
That is a good question, though.
Well, I just kind of got there because I didn't know what pressure enters turbine 2, or if we even need to know that.
Yeah. So so you have a lower pressure coming out of turbine 1, and it goes into this, steam generator. And I really do think that is somehow constant pressure. And so whatever the pressure is coming out of that first stage turbine, that has to be the pressure going into the second stage turbine.
Yeah, because here, even for the original cycle, we have from stage 4 to 1 isobaric boiler written down, which the reheat is just another boiler, right? So.
Right. So.
Yeah, isobaric condenser and then isobaric boiler.
Right. Yeah, the question is, so like it.
Yeah, because he's right too, even just the original boiler, it being isobaric, you'd think, liquid going to vapor, the pressure would be changing, but well, then again, as it's boiling, I assume instead of the pressure going up, the vapor flows outward.
Yeah, yeah, maybe it's something like that, so the volume's going up, but that volume going up is what's pushing the stuff along back to the second stage turbine. I don't know.
Yeah, because as it evaporates, well, I should say, as it is superheated to a vapor, instead of the pressure going up, mass flows through, which would make sense.
It seems to make sense to me, kind of. So yeah.
Yeah, steady state, so then the pressure stays the same.
Yeah. Okay. Well, let's call that our working hypothesis for now. Okay, that's all. No more questions.